Welcome back to The Explainer. Today we're treating this like a high-stakes mission briefing because we are unpacking a radically secure computing paradigm known as yubiOS. If you've ever stopped and wondered who actually holds the ultimate authority over your machine's lowest-level operations, well, this analysis is going to completely reframe how you think about hardware trust, OS immutability, and honestly, device ownership itself.
The core cyberpunk ethos driving this entire project boils down to one simple, aggressive idea. No TPM, no OEM, no trust anchors you don't control. yubiOS is an experimental, FIDO2-first, immutable Linux operating system. It represents a massive shift away from those external corporate dependencies we're all so used to. It basically challenges the status quo by insisting that the machine owner's physical hardware key, specifically a YubiKey, should act as the absolute root of trust for human presence and identity. Okay, here's our agenda for today. 1. The hardware sovereignty vision. 2. Architecting a sovereign OS. 3. First boot enrollment flow. 4. Engineering milestones achieved. And 5. The hardware horizon. Let's get right into it.
Section 1. The hardware sovereignty vision, the paradigm shift.
Now, in conventional architectures, your trusted platform module, the TPM, serves as the primary hardware anchor, right? But here's the catch. Because it's integrated by the OEM and managed through closed-source firmware blobs, it's a trust anchor you can never fully verify yourself. yubiOS completely flips this equation. It requires owner-signed kernels and elevates the YubiKey to act as the absolute user-controlled root of trust at literally every single layer of the stack. Hardware sovereignty isn't just some flashy buzzword here. It's a rigorous security model. It dictates that the absolute root of trust for human presence and identity resides solely in your physical control, entirely eliminating those external proprietary dependencies. You aren't trusting some OEM's keys. You're trusting the physical hardware security module you actually hold in your hand.
Moving to Section 2. Architecting a sovereign OS, deconstructing the stack.
So yubiOS is heavily inspired by the immutable ecosystem, which is this big push toward image-based, deterministic Linux workloads led by the engineers behind systemd, composeFS, and Flatcar. Let's look under the hood at the open-source components powering this thing. For image delivery, it's using bootk for OCI native deployments. File system integrity, that's guaranteed by dmverity and composeFS, meaning your root file system is mathematically verified to be read-only and tamper-proof. It uses systemd repart for partition generation on first boot and handles AB atomic updates via systemd sysupdate. And right down at the very bottom, replacing traditional platform defaults, is the YubiKey handling FIDO2, PIV, and Oath protocols as the independent root of trust. Because this system is OCI native, it treats your operating system the exact same way modern infrastructure treats containers. You can pull verifiable atomic updates straight from a registry. But yubiOS goes even further by leveraging strict policy as code during the build phase using a dedicated Rego file. The CI pipeline produces images with SLSA build provenance and full software bill of materials attestations. It's almost like a cryptographically sealed chain of custody for your code. You get a verifiable trail of evidence for every single component in the OS before it ever even touches your local hardware, which absolutely guarantees total integrity across the entire root file system. Section 3. First boot enrollment flow. Demoing the flow.
Now this part is a massive security advantage. See, traditional OS installations often provision partitions and generate encryption keys outside the target device, which obviously creates opportunities for secret leakage during manufacturing or distribution. yubiOS ships a minimal disk image. All the remaining partitions are created and encrypted locally by systemd repart running straight from the initard on your very first boot. The cryptographic key material for the root file system is generated directly on the target device, and it never ever leaves it.
So on that first boot, an enrollment wizard runs automatically on TTY1 to establish the trust chain. It basically guides the owner through 4 idempotent steps, which you can totally skip if you need to. Step 1 configures the UEFI firmware to accept the owner's keys, signing the initial unified kernel image. Step 2 binds the root and user partitions directly to the YubiKey via FIDO2 Hydra. Step 3 creates SSH resident keys that physically live on the YubiKey for highly secure remote access. And Step 4 sets up PAM U2F. That means you literally have to physically touch the YubiKey for any sudo operation or local login.
And here is the absolute crucial piece of this puzzle, PIV slot 9C. When we talk about secure boot in yubiOS, remember it requires owner-signed kernels. Unlike standard FIDO2 operations, which use the HID raw interface, this secure boot signing specifically leverages the YubiKey's PIV, or Personal Identity Verification, slot 9C via the CCID protocol. This allows the YubiKey to act as a cryptographic signing token for the OS image itself. So no unauthorized kernel can be booted, regardless of where it came from, because the signing authority is literally sitting in your physical pocket.
Let's hit Section 4. Engineering milestones achieved, flexing the progress.
Looking at their rapid-fire CI milestones, the foundational tooling is actively crushing these rigorous checks. Sprint 1, they confirmed MKOSI PIV signing matches upstream systemd capabilities perfectly. In Sprint 2, the virtualization kit, BCVK, successfully passed virtuoFS root bootloader update guards. And crucially, for Sprint 3, native bootc install paths directly to the file system were verified and tested cleanly on both AMD 64 and ARM 64 architectures.
And to prove these claims out in the open, they rely on automated, cryptographically backed CI evidence. A huge milestone was run 2987-2832727. This run proved that the root SSH credential path functioned flawlessly, successfully authenticating and running assertions inside an ARM 64 virtualized guest. This kind of hard proof is exactly how yubiOS validates its progress. To gear up for real hardware, the team executed Phase F0, which is a QEMU-simulated ARM 64 bring-up. They successfully built a simulated boot chain that brings up a yubiOS-owned firmware TPM. This stack includes trusted firmware A managing secure world transitions, the OPTE secure operating system, Microsoft's reference TPM 2.0 running as a trusted application inside that secure world, and finally an open-source uboot bootloader. They are literally simulating total ownership of the lowest level firmware. It's wild.
All right, Section 5, the hardware horizon, the next frontier.
So why is ARM 64 the primary target here? Well, with standard x86-64 processors, while yubiOS fully supports them above the unified kernel image, your platform firmware and the TPM remain OEM-supply proprietary blobs. You can never truly own that bottom layer. But by targeting ARM 64 as primary path A, yubiOS opens the door for total ownership of the secure world firmware stack, integrating that fully open-source TFA and OPT stack we just talked about. To translate all this simulated progress into physical, real-world hardware sovereignty, the project is actively targeting specific single-board computers. The ROTSA ROC5B is the primary path A board, with the ROC Pro 64 stepping in as a supported secondary. Their next immediate engineering challenges involve rehearsing the physical fusing of the root of trust public key, the ROTPK, on sacrificial hardware and sourcing verified, immutable DDR blobs so they can finally flash this perfectly owner-controlled stack onto real silicon.
We've seen how yubiOS is basically taking a sledgehammer to the traditional walls of OEM-mandated trust. It replaces closed blobs and external TPMs with cryptographic proof tied directly to a physical token in your pocket. From immutable OCI native deployments to completely owning the ARM 64 secure world, this project forces us to rethink everything about device ownership. So, as we wrap up this explainer, I want to leave you with one final, slightly unsettling thought based on the exact hardware you are watching this on right now. Who really holds the keys to your system?